Hi, welcome to another edition of Calculus 3. Today we are going to continue our conversation about differentials. We are going to approach this from the point of view of a demo, hoping that it will help in understanding the topic. Let's go ahead and look at the description of the problem in 2D from Calculus 1 again. So suppose we have a function, say our basic parabola y equal to x squared, and we are studying how it changes. So we could be at the location x here, and the height is this blue line at this location. Suppose I move x to another location. So this is going to be my new location. Let's call it x plus delta x or x plus dx. These are the same thing. Delta x and dx, we said it represents our increment in x. So at this location, we have a new height. We want to be able to predict this new height in terms of the original one. To do that, we can, of course, just insert our new x value into the function, and then we are going to have a new y value. This is referred to as y plus delta y. So y plus delta y, the delta y represents the increment in y itself. Now, to have an approximation for delta y, we said that we are going to consider the tangent line at the startup position and see where that goes. So let's suppose we take a tangent line and let's assume that this is the intersection of the tangent line at this point. So what we are going to do is to consider this point as an approximation for this one. So the exact one is y plus delta y, and this one we are going to show it by y plus dy. The relationship between dy and dx is that the ratio is equal to the slope of a tangent line at this location. So what we have is that the slope m or f prime of x is this dy to dx. So if you want to look at it from the differential point of view, we can say dy is equal to f prime of x times dx. And delta y is approximated by this one, by dy. Now, in three dimension, let's consider a comparable function here, say y is equal to x squared, z equal to x squared plus y squared, or something like that. In the demo, I'm going to have this divided by 2 so that the function is a bit more flat. We have a surface, in this case a paraboloid, so it's going to look something like this. Now, if I have some location, xy location here, and go ahead and find out what the height of the function is at that point, that's going to be our base of our operation. So this is some point x and y at which we can find the height of the function z. Then I change x and y. So x could be changed by some value. So now my new location is x plus dx or delta x. And then in the y direction as well, this is going to be y plus delta y or dy. And When I change both x and y, I'll be at this location. So this one will be x plus delta x in y plus delta y or dy. So in this case, we have not changed the x, and in this case, we have not changed the y yet. Now, what we do is that we go ahead and find the new height at this new point. So at this point, we go straight up, and perhaps we hit our surface at this location. So this location is going to be location z plus delta z. If we want to do the same thing that we did over there, that is, we had approximation of our increment by a tangent line. Here, we have to use the concept of a tangent plane. So I have to consider a tangent plane that is tangent to the surface at this location. So suppose something like this. And find the intersection of that tangent plane with this vertical line, wherever that is, wherever that intersection is. Let's use a different color. This is going to be the location z plus dz. We said last time that the differential dz is partial of z with respect to x times dx plus partial of z with respect to y times dy. What we want to show in this demo is where does this formula itself comes from, and how does this tangent plane plays with respect to our surface. So let's go ahead and see if this demo helps us see what's going on in this situation. So here I have that paraboloid that we're talking about, z is equal to x squared plus y squared or something like this. This yellow plane is our xy coordinate plane. And here I have a location x and y at which a height is evaluated. Now from this point I move away by a small amount in x direction, another small amount in the y direction, and at the intersection I have my new location. The coordinate of this is x plus dx and y plus dy. At this new location, we want to know what's the value of the function. Value of the function will be this height. Question is, what's the relationship of this height to the original height? We have gained some extra height, which is going from here to this location. That we refer to it as the increment in z, show it by delta z. The question is, how can I approximate this delta z? The way we do it is that we draw a tangent plane at our starting position. So this blue plane is to indicate the tangent plane here. This tangent plane is going to intersect this vertical at this location. At this location, we have the intersection. So this is an approximation for where we want to be. Because of the curvature of the surface, this curves away, and there's a gap between the two of them. Of course, that's a source of discrepancy between delta z and dz, but the differentials help us to quickly calculate an approximation for where we want to be. Let me turn this thing around so that you can get perhaps a better view of what's going on. So again, this is the paraboloid. The yellow plane is the xy coordinate plane, and this bluish green one is the tangent plane at the starting position. So if I go ahead and perhaps turn this around some more, this was our x, down here is our original xy, and when we go straight up until we hit the surface, that straight line is going to be our z. We are changing x to a different location, changing the y different amount, and here we are changing both x and y. At this location we are going straight up until we intersect with the surface, and that again is our new z. This is same height as the old original z, and from here to this location is going to be our delta z, or increment in z. From this location to the intersection with the tangent plane is going to be our dz, or the differential of z. So of course if the amount that we move away is shrunken to a small amount, then the, the approximation and also the new location on the surface is going to approach the original location. Here, for example, we can see a little bit of this demo where I get closer and closer to the original. So in this case, you see that delta x is becoming smaller, delta y is becoming smaller, and my height is coming close to the original height. We still see a gap between what delta z shows. Delta z goes all the way to the surface. dz, or differential of z, that's where the tangent plane, this blue plane, strikes the vertical. The gap between these two locations is the error we are committing by using differentials as opposed to the exact increment. So, of course, I can change my location here. If I go around, my tangent plane also moves around with me. So I can go around my surface, and my tangent is just sliding over the surface as I go around. Same thing happens at any location. I can change my y value same way. I can move it y quantity back and forth. My surface again stays tangent to the my tangent plane, just slides over the surface, and same principle holds in all locations. So when we are writing this formula dz, partial of z with respect to x times dx, and partial of z with respect to y times dy, what is it that we mean by it? Well, if I take, for example, z to be x squared plus y squared, in this simple case, partial of z with respect to x, we can either write it this way or more abbreviated in that style, is the derivative of this with respect to x. That is just 2x. In the same manner, partial of z with respect to y is 2y. What are these two quantities, 2x and 2y? These are the slopes. So let's go back to our picture here. Let's magnify this slightly so that we can see. So when I change my x, here's I'm changing my x, my z changes, and the slope at which I am changing my z is going to be partial derivative of z with respect to x at this location, which we calculated to be 2x. So the effect of changing x is reflected by this increase in z. If instead I change y, keep x fixed and just change y, then the change in z is reflected by this ascent going up in this direction. So these two that I just showed you are these two, the slopes of those two lines are the values of 2x and 2y at the start of that trip. That is, when I go here at this location, if I calculate 2x, I'll get the slope of this line. If I calculate the 2y, I get the slope of this line. When I change x, there's a rise in the value of z. When I change y, there's a rise in the value of z again. When I change both x and y, these two increments get added up, and I arrive at this location. So moving on the tangent plane, we are changing x going up in this side, changing y is same as going up in this side. If you are changing both of them, we are going to travel on this figure that looks like a parallelogram, and we end up at the opposite corner of the starting corner. So this is our starting place. X is increasing here and y is increasing in that direction. And this is the net increase when both x and y are changed. So we are emphasizing this concept here because pretty much all engineering calculation, or at least all continuous type engineering calculations, rest on the concept of differentials. So this is the building block of just about any advanced engineering calculation you're going to do against of the continuous type of calculations. So it's very important to gain an appreciation for what the differentials are, what role they play. It's just an extension of the concept of the slope that we had in calculus 1, but we need to have a picture in our mind about what is happening here and what is it that is being calculated, and be able to appreciate the meaning of mathematical calculations that we do. Okay, so so let's go ahead and again just as an exercise, let's do an additional case of calculating a differential. You remember we refer to this thing as a total differential. And so if I have another function that would be another surface, let's go back to another color, z. Suppose I have, say, x squared plus 2xy plus, say, y squared. So in this case, z sub x will be 2x plus 2y. Z sub y will be 0, and this is 2x, and again 2y. So our dz in this particular case takes on a very simple look. It's zx, which is 2x plus 2y times dx. And then, again, accidentally in this case, these two became the same, and I have that times dy. So if I want to calculate the differential at any particular location, I need the x and y coordinates of the starting position. I need to know what the increments dx and dy are going to be, and when I plug it here, I'll get my total differential. So this is what is called total differential. So I hope you spend a bit of time on this. Make sure you understand what is it that we are doing here, aside from mathematical formalism that happens here. This is pretty straightforward. Understanding what is happening in the picture, that's a very significant achievement for students to appreciate the picture itself, and that's going to help you with many other calculations that you're going to be doing later on. Okay, so we are going to have a short lecture today, and good luck and God bless until the next lecture.